Sup guys, welcome to today's show. So today we're going to continue our HTML project, and in the last episode we finished our lexer, which means we are now able to turn our HTML code into tokens. So the next logical step is to write the parser. And the parser in this case will simply be something that goes through a list of tokens and creates a stack. So basically, let's say we have this code. Seems to be lagging a little bit. It's difficult to write. And then we have a text token. Let's say hello world. Then we close it up. So this will be transformed into the specific tokens. Tag start, text token, tag end. And that we know all about already. But when we parse these tokens, I want to create a stack-like structure, but not entirely so, because a stack has two operations, push and pop. When we push something to the stack, we put it like this. So we push the first token, then we push the second, and the third. And then usually we might pop something. And then the last thing that we put onto the stack will be the first to go, like this, and then this, and then this. So that is how a regular stack works, like the memory of a function, let's say. But I wanted to do it slightly differently, because we could do it like that, but then we would run into trouble if we, for example, wanted to create an HTML, which, let's say we have a B tag, and the logical thing would be to close that B tag here. But let's say that we, for some reason, closes it after the body. This is valid HTML, but the stack wouldn't be able to handle this, right? Because when we get here and we pop the last thing, it will pop off this one instead of the body. So we will have a special kind of pop. Let's call it a pop for alternative pop. And it will take an argument, which is a token. And this will pop off the last token of that kind. So let's say we have this stack body. We can have the B as well. And then the text token. And then we do an apop body, because that is what the code says, right? And then we will search to the stack in this order until we find the body, and we remove that. And we might have like 2 Bs or something, which also is valid HTML. And let's say we come down here. That means we want to pop off this one. And when we come here, we want to pop off this. So these are the 2 operations, push and apop. And when we encounter a text token, so let's remove this from the stack, and we will not put text tokens on the stack, by the way, and I'm going to tell you why. So let's clean up this code a little bit. Let's remove these B's. So this is, by the way, let's put it back. It's a better example than doing something with the HTML of their body, because they don't really do anything, right? So our stack looks like this when we encounter the text token. And every HTML tag will link to a function. So let's say this HTML has an HTML function. Body has a body function. And B has a B function. So when we encounter a text token, we look at the stack and we run the B function on the text token. And then we run the body function on the text token and the HTML on the text token. So we will run every tag function on that text token if it's on the stack. So let's say we have a foo bar down here. So we'll run all these 3 on the hello world text token. Then we come to this B. So then we'll do an apop operation on the B. And when we hit the foo bar, we will only run the body and the HTML on foo bar. And then these 2 closes, and we apop them. So in that way, we will be able to affect the text tokens based on what's on the stack. Simple enough, no? I think this is a rather elegant solution. Okie dokes. So let's run a parser, shall we? Let's write a parser. And I think we deserve a new file or 2, perhaps. So let's create a parser.c. And a parser.h. And let's also modify our makefile accordingly. So we'll have a parser O depending on parser.c and parser.h, which will run cc with the flags on the input file. And then we link with the parser. When we have this nice looking structure in the makefile, it's very simple and easy to add new files. So let's double check that we have the new files. Parser, yes we do. And if we try to compile with these new additions, it works. All right, so what shall these files contain? Well, before I forget, let's also include the parser here. And I don't really like these what's it called? Quotes. I think it looks a little bit more serious when we have it like this, right? So let's do that. And let's see the other files as well. This looks okay. This too. Here I want to change these. And let's add the pragma. Let's also modify this one. And for you beginners out there, the difference between having these brackets around the header file and having the quotes is that the quotes, then we are looking for files inside of the current folder. And when we have brackets like these, we usually look at the operating system's default include directory, where all the standard C libraries and stuff is located, the library header files. On my system, it's inside user include, but that depends. However, we can add our own directory in addition to the default one. So we just do dash big L, and then we put the directory, and we can put a dot for the current directory, which means that this should compile now. It does not. Sorry. Big L is for the library files. This should be big I for include files. Now it works. Nice. It's starting to be quite a big project, this. Alright, so let's write a parser, shall we? Right after this. Did you learn anything useful today? And do you want to support this channel? Go to drbirch.com/support. You can also click the button Become a Member. Thank you for your support. Alright guys, welcome back. So let's start writing our parser. And as usual, I will begin by defining the types. So let's start with the stack structure. So we'll define a, first, what should we call it? Tag stack, perhaps. Or no, let's just call it a stack. So we will have an S stack. And what shall it contain? Well, we need to make it a linked list. Or we don't necessarily need to, but I think I'm going to. It gives us the most flexibility. And this will be a list of tokens. But each stack structure will only contain one token. So we will have a token shall we make it a pointer? Yeah, I think we are going to, for now at least. I can't really decide. Let's not make it a pointer. So we'll have a token, and we will have a struct S stack next. And I think we will make it a dual directional stack. Dual directional linked list, I mean. So we'll have a next, but we will also have a previous. So we can go both up and down our list. And I think this will be all we need for now, at least. Maybe we should put the function here for convenience. So let's say we have a type definition for a function. And it will return one of our string structures. Like this, I guess. And the arguments, I'm not really sure what that's gonna be. We will probably have a token at least. Let's just say we have a token. It will probably be more things later on, but we just need a placeholder for now. Let's also include hyper.h. Let's say we have a function fun. And we type def struct s stack, and this will be a stack with a capital S. Alright, and we will have a constructor. So it will return stack pointer, make stack, will we create it empty to begin with? Yes. And then we will have the two operations. So we will have a push. Push operation, which will take a stack, and it will take a token, and it will return the new updated stack. So we also need to give it the garbage collector so we don't leak memory. And our apop will also have a garbage collector, a stack, and a token type is probably enough. I think. Well, let's start there. So we need to have this constructor, make stack, no arguments. Why is this erroring. Because it can't find this. It doesn't understand the make file. Maybe we can do this while we're developing. Just for convenience. I will change that back later on. Right, so we'll have a stack P. And we want a size. Size is equal to the size of a struct as stack. And then we malloc. Let's assert that we have a P, and then we zero the P. With the size. And we return it. Simple enough. Let's also be a little bit explicit. Or never mind. So the next operation is the push. And before we can write that function, we need another function. We need to find the last entry in the linked list. So let's call this find last. It takes a stack. Find last, we have a stack S. And we need a pointer. So we set P equal to the first in the list. And as long as there is a P next, we won't loop. And P will be equal to P next at each iteration. Then we should just be able to return P. Yeah. And if we don't have an S, we'll return 0. By the way, let's not dereference this. Alright, so now we should be able to write our push, which takes garbage and garbage G. It takes a stack S and let's see the order, and then the token T. Alright, let's also include tokens.h. And let's assert that we have a G, or not a G necessarily. Let's assert that we have an S at least, and that we have a T type. And we need to have a pointer as well. Two, actually. We need to have a pointer for the last entry. And this push operation we will handle differently depending on, let's see, if the stack is empty. Well, we can do something like this. If we don't have an S next, that means no, it does not. Because S next is 0 if we have an empty stack, but also if we have a stack of length 1. So how do we differentiate? Let's say if this function is empty, then it's a first. So then we have an empty stack. Maybe we should create an alias for that, just to be more precise. So let's define empty x so x fun is equal to, now we can do this, so if the function of x is 0, then we have an empty stack. So if empty s last is equal to s, otherwise last is equal to find last of s. And we want to allocate maybe we should create this in the functional style, like we have done this far. So we create a new list each time. Which means that we will have an S prime instead. And if S is empty, last will be S. No, S prime will be make stack. So create a new empty stack. And last will be equal to that. And if it's not empty, S will be equal to stack copy S, G and S. And last will be equal to find last of S prime. So we operate on the new structure. And if we have a G, we add our old stack to the garbage collector. All right. We need to create this stack copy function. So how do we copy a stack? We need to have a pointer. We need to assert that we have an S. And we need to have a new thing. So we'll have a for loop where we set P is equal to the S. We'll loop as long as we have a P next. And P will be equal to P next. But if we don't have a P next, then this stack is empty, or might also have a length of 1. Maybe we shouldn't do P next here, just P. And same here. And if our S is empty, we can just let's remove this garbage here, by the way, because I don't want to get into the occasion where we add it here and then here as well, and we have all different kinds of trouble. So the push and the pop functions will handle the garbage collector. Alright, so P is equal to S. But if we have an empty S, all we need to do is return make stack, because we will return a new empty stack. But if it's not empty, we want to loop. And what do we want to do at each iteration? So let's see. We need to create a new stack. So new is equal to make stack. And we'll need to have a see, what can we call that? Let's call it latest. It's not entirely accurate, but close enough. And we set latest to 0. We make a stack. And the new function should be equal to the old function. We want a memory copy into the new token. Do we have a copy function already for tokens? I don't remember. We have a T copy, but that's for a tokens pluralis. So I suppose we need to do this manually. So we memory copy into the new token. From the old token. But these aren't pointers, so I suppose we need to put the address like this. And size of struct s token. Alright, so that's for the token and the fun. What about the next and the previous? Well, the next we can't set quite yet. But the new previous should be equal to the latest. And then latest should be equal to this. But before we assign it to new, we should also do, if we have a latest, we should set the latest next to the current, like this. I think this is the right way to do stuff. And now we should have a copy of this linked list. So we return the new. But this new keeps changing. So we need to have a first, I suppose. And let's set first to 0 from the beginning. And if we don't have a first should be the new. and then we return the first. Okay, now I think it's right. So we make a copy. Last is find last. So the S prime previous should be equal to the last. No. After we have our coffee, we want to create a new one because we need a new entry. So P will be equal to an additional new stack. But only if S prime is equal to last. So if we are at the first entry, we don't need to create a new. We can just point P to S prime. Otherwise, we need to create a new. Now we can set P's previous to last. But if this is the first, previous should be empty. Maybe we should set last. No. Okay, we need an if statement here as well then. Or let's do it like this. So previous should be set to last, unless this is the first entry. In that case, previous should be empty. In both cases, next should be empty, because we haven't gotten that far. But if we have entries, we want to set the last next to P. And now we can populate this thing. So we can memory copy into p token from the t that we supply as a parameter to the function, and size of struct as token. And by the way, when we do this, we probably need to cast this to int 8. And then we have the function. So we probably need to create a function or a macro or something which matches a function from the HTML tag. So let's just for now say that pfun is equal to find function, and we give our t. And if we don't have function, if find function didn't find anything, we want to default to a function called id. And id should have the same signature as this, which we don't really know at this point, but well, we need to give a string as the argument as well. So we will have an ID. This is an identity function which basically takes the input and returns it. So it does nothing. So let's say we have a string s and a token which we don't need. So let's just do this. And let's code this function. Pretty simple thing. It will be a string ID. So we have a string s and a token nothing, and we return s. So let's temporarily define this find fun thing. So it will return a function. find fun. It will take a token T. And for the time being, no, that's not right. For the time being, we will just simply return zero. But this is temporarily. All right, I think it's starting to be time for testing this stuff. We can use what we have. Let's just create a token and let's set the token to x's, t's, and the first one. We probably want to do this. And let's create two. So we will have a stack old and a stack new. The old stack should be equal to an empty one, and the new should be equal to push operation of garbage and old and the token. And let's just print something from that thing. Let's take the address first. And if we have new, let's also print something from the token, perhaps. Let's print everything. So let's do one at a time. So we have token, fun, next, and previews. And for the token, we can do new token contents text token. Oh, let's do tag start, because this is a tag start. And then we have, is it data or starting to be a lot of different things. Hard to remember. So we have a tag star value, okay. Tag start value. So that's one. Token and fun. We can print the address of the function. So new fun. And then we have next and previous. Same there. New next. And new previous. Did I miss something? Yes. No. Oh, this is a wrong direction. Now it's better. Alright, I have no clue if this is going to work. Let's see what the compiler says. Okay, not that many errors actually. Conflicting types for scopy. Stack. Scopy. Stack star, scopy, stack star. Stack star, scopy, stack star. Why is that the conflicting type? Do I have another scopy perhaps? Yeah, that's probably it. Let's call this stack copy instead then. Okay. Union Anonymous has no member name tag start. Did you mean start? Yes, I did. Thank you, GCC. Oh. Unknown type token. 970. Passing over with one stack incompatible type. Right. We shouldn't pass the garbage collector any longer. In 97. That's right, because we're not really finished here, are we? We need to return P. Oh, I have a feeling that this will crash so badly. Huh. It didn't. It actually seems to work exactly as it should. But does it work if we push another thing to it? Because that is handled differently. So let's create something called middle or something. So the old is make stack. Then we have middle, which pushes the T. And then we have the new, which pushes middle and T plus 1, say. Then it crashes. We had to have a crash. Okay, so it works when the stack is empty. That's something, at least. So what are the specific things for a non-empty? We set S prime to stack copy. And we try to copy something of size 1. And what will happen then? We will have an S. It's not empty. How do we define empty, by the way? No function. So latest is 0, first is 0. P is S. Do we have a P? Yes. We create a new. If first is 0, which it is, first is new. New fun is P fun. We do a memory copy into new token. From P token of this size. We set the new previous to latest. And what is latest? Latest is 0 at this point. Shouldn't the latest be the current one? Let's see. We create a new thing. It might be the first thing. And if it's the first thing, previous should be 0, which it is. And then it's new. I think the stack copy succeeds actually. Let's see what's the last thing that happens. We malloc 4 times. Let's ask GDB. It's in the push. And we try to move something into memory from EBX. DS and this. Isn't this trying to move it into this address then, in memory? It's a weird address, C. Let's see, A is 10, B is 11, C is 12. What is this? Zero. This is just in the beginning of the function. No, it's not. It's just after the call to 0. but I don't see any call to 0. Maybe it's an optimization, inlining or whatever. Let's alter the make file slightly and remove all optimizations so it's a little bit easier to debug. Okay, now it looks different. Maybe we should do this instead. X30i EIP. Okay, so what's the next thing that happens? Some push operations and then memory copy. So it's before memory copy that we crash. That's useful information. Memory copy is here. P next is 0. Okay, this looks better. So here is a call to make stack. And then we just move around different registers. Make stack. So we are here or here perhaps. But probably here, because if we were inside of all of these if statements, we would see some jumps and stuff. And the only jump we have is this. And then it's the call to make stack. This jump is to 180. So no, that's not it. Make stack. We are here. P previous is equal to last. Is it possible? No. We should be able to set P previous. What about last next? Can find last return 0? Yes, it can if we don't have an S. But we do. But maybe we don't have an S prime. Can stack copy return 0? First is set to 0 and we return first. So is it possible that it still is 0? Maybe we can check the return value. If we break here, okay, so now we should see the return value instead of EX, right? Okay, it does return something. Okay, so it seems to return a stack. But it's all zeros. So we do a stack copy, we set last to find last. So what happens if we give the stack, the find last function an all zeros stack? We do have an S. So we set P is equal to S. Do we have a P? Yes. P is equal to P next, which is 0. And then we return that 0. Maybe we should do, if we have a P, we return a P, otherwise. should probably return S, right? Okay, now it works. Easy peasy. Really nice. And if we print the next and previous of not new but middle, I don't like that the next is 0. Wait a second. P next is 0. And what is P? P is the new thing. But we shouldn't return P. That's the problem. We should return the first thing in the new list. So we need a first. And if it's empty, first is S. Otherwise it's still less. So we can just return S prime instead. We don't need a first. Hope this works. It's annoying. Everything seems to work perfectly, but we don't set the next, and I don't like that. We will return S prime, which should be the first in the list. Because we return the first here. The first is a new, but only if first is 0, so it should only set it to the first. What if we remove this? No. Last next is equal to P. Maybe we should have a case here anyway. So P previous. What happens if we do this? That's a bit unexpected. P is equal to S. I think the solution to this is we need to create a length function so we can make these cases a little bit better. Yeah, let's try that after this. Be right back. Did you know that I made a book about computer networking? You will learn how the internet works and how everything works under the hood. It's a complete beginner's course, but it has some advanced elements as well. And you will learn network design and network security and all different kinds of stuff. For more info, check out books.drbirch.com. That is books.drbirch.com. Thank you for your support. Sup guys, welcome back. I'm not really satisfied with the way I wrote these parser utility functions, so I'm going to rewrite a couple of those. But first I want to add to this structure, I want to have length. And I want to rewrite this, let's see, the make stack, giving it an argument. So we'll give it a length and we'll create a linked list of that length. So first we will create an empty structure and then we will fill it with data. I think that's a better way to do stuff. So let's see, those two we can keep. Let's move them to the top. And find last is a simple function, we can keep that. So then we have the make stack, the stack copy, the push. Let's comment these out for now. Maybe we'll use some of them or some parts of them, but for now let's just comment it out. So let's see, make stack, and we will have a size. No, wait a second. Let's keep this, but let's call it make entry instead. So stack make entry, and this will return. This will create a single entry of the linked list, while the make stack will create the entire list. So how do we write this new make stack? Well, as I mentioned, we need a size. And let's see, do we want it to be we would like to create an empty structure? Yes, I think we do. Or not a completely empty. It needs to be at least one. So let's do a for loop. And let's have a counter. We set n equal to the size. Loop as long as we have an n and we n minus minus. And at each iteration, make an entry. We need a last. And our new entries, previous, will be our last. And our new last will be this one. Before that, we set our last next to this one as well. And we need to save the first entry. So if we don't have a first, this would be our first. Then we return it. Simple enough. Let's also create a print function. I will not make this as involved as I did the show tokens stuff, because those we might use in our code. This will only be for debugging. So let's create a print stack. Let's wait a little bit with that, by the way. I want to create an index function. So it will return a stack. We'll give it a stack and an index. So we can index into like the first entry, the second entry, and so forth. So stack index. We will have an S and an index. Maybe we should name the function index like this. By the way, we need to set the length of this thing. So the first, and the length will only be at the first linked list. So first length is size. I don't think I want an int 16, by the way. I want a signed short int, because I want to be able to index into -1 as well, which will be the last one then. So signed short int. We need to assert that we have an S. Let's do separate. We assert that we have an S. We assert that the length is greater than the index. And if the index is less than 0, we want to do one thing, otherwise we want to do something else. So let's start with something else. We'll have a for loop where we set n equal to 0, or no, n is equal to the index. And as long as we have an n, and in this case the index is positive, maybe we should go the other direction. So let n be 0. And as long as n is less than the index, we'll increase it. We will also set our pointer to be equal to the first stack. At each iteration, this should be equal to next. Maybe this is all we need. And if the index is less than 0, we want to set n equal to 0. We want to set p equal to not s, but find last s. And we want loop as long as n is more than the index. We'll do n minus minus, and we'll do p is equal to p previous, so we go backwards. So if we have -1, n is 0 and index is -1, so n is more than index. It will return the last one, yes? And if, no, we don't need an if, I think. We should just be able to return p in this case. Okay, so that's an index function. Now it should be pretty simple to create our stack copy. And I think I do want to have the garbage collector here. So let's assert that we have a G. No, we don't need to assert that. But we need to assert that we have an S, and that we have a length. In that case, we can create a new stack of size length. And now we just need to go through that and copy everything. So let's double check that we have one of those. If we don't, we return an error. And now we just need to go through the brand new stack structure and go through the old one and just copy from new to old. So let's have a new pointer and an old pointer. We'll make a for loop. We set n equal to 0. We want to loop as long as n is less than the length. We want to set the new pointer equal to the new and the old pointer equal to the old. At each iteration, we want the new pointer to be equal to the new next, and the old pointer to be equal to the old next. And then we can do something like copy entry. We copy into the new from the old. And one more thing. At each iteration, I want to add, if we have a garbage collector, I want to add to the garbage collector the old thing. And what is this copy entry thing? Well, let's define it as a macro. So copy entry destination source. And we want do. So what do we have inside of these? We have a token, a function, and at the first location we have a length. So let's start by setting the new length. No, we don't need to do that because we do that in our make stack, don't we? Yes. So all we need to do is first of all copy the token. So memory copy to the address of destination. From the address of source. Size of, no wait, it should be destination token. Source token. And size of struct s token. And let's also set the destination function equal to the source. The source function. Okay, I think this is going to work. Let's put it into our H. And when we have added, copied everything, we should just be able to return the new thing. And let's go back to this print function. So void print stack. We need a stack. And we need a pointer. We need an n. So we set n to 0, p equal to s. We loop as long as n is less than s length. at each iteration n plus plus, and p is equal to p next. And then we print a bunch of stuff. Something like this. It will be pretty similar, but I will only do one printf for everything. Something like this. And what do we have? We need to have the P. And the P token contents. Let's do text token like we did before. Value. And then we have the P next. And P previous. Like so. And then we return. So that's our print stack function. And we have index, find last, stack copy. Yeah, I think we can create our push function now. And it should be fairly straightforward, I hope, with all these additions. So we'll create our push. We'll take a garbage collector. We'll take a stack. And a token. We assert that we have a stack and a token type and a stack length. So first we make a copy of this thing. Maybe we should name them. Yeah, let's call this S prime so we know it's a new thing. S prime will be equal to stack copy garbage S. If we don't have an S prime, we'll return error. So when we have this new copy, we want to create a new blank entry. And we want to set let's create the last as well. So last will be the index of our new stack -1. And our last next is our new thing, the entry. And our entries previous is the last one. And our new stack will have a greater length. And then we'll just do a memory copy. Or let's do a copy entry. The destination is our new entry. And the old, well, we don't have an old for this, do we? No, we need to do this manually. So we memory copy into our entries token from our T, size of struct as token, and then the function. And the function would be, let's see, entry fun is equal to find function T. And if we have a G, we can run the garbage collector. We don't need to care about the return value. Or do we now? Possibly. So let's do this. And we want to return our S prime. Okay, this function was a little bit easier to write than the last one. Will it work better though? So let's see, what do we have here? We create a new stack of size 1. And we set the function equal to find function based on our t. Let's wait with this middle thing. Let's do a memory copy into our token from our, let's see, from our T, like this, I suppose. No. Or yes, I think that's right. Size of struct as token. So now we have one thing. Then we call new, and we push onto our other token. Then we can print our stack, new stack. We can run our GC, not caring about the return value, and return. All right, let's see how this will be after we have cleaned it for errors. Conflicting type index. We stack sign short int. Stack sign short int. Maybe it is. Maybe there is already a function index. Yes, there is a deprecated function index. How can we make our index take precedence? Maybe we can. What if we make it static? Will that make a difference? Nope. It's included from string.h. Do we really need that thing? I don't think we do. Let's remove this. Middle is an unused variable. I don't care. Warning: index declared static but never defined. Static stack index. Static stack index. Why does it say that? Oh, it's when it's inside of the hyperbird. We need, but we are including the parser.h. Wait a second. We don't have access to the static things, of course. Let's do this the old-fashioned way. S is a pointer. Oh, I forgot the 4. Up is a pointer. Oh, what's this now? Unknown type name string parser.c. So where do we have this? Well, we need to include hyperbird.h. probably the rest as well. Let's take one at a time. Huh, it compiled, but will it work? No, segmentation fault. But I'm not really surprised. Okay, we zero out some big thing. Let's see where we're at in GDB. Make stack is crashing. So we're trying to move into memory the contents of EDX. What do we have there? Something which is empty, but more interestingly, what do we have inside of EX? A 0. So let's see. Make stack. Last is 0, first is 0. N is equal to size as long as we have an n minus minus. We make an entry. If we don't have a first, this will be our first. Our previous will be last, which is 0 from the beginning. And if it is 0, we can't do this. So let's double check that we have a last, and then we do this. Let's see what happens this time. Still seg faults, but perhaps at a different location. Yes, now it's in the print stack. Similar error though. So we have a 0. And it's right before the print F. So n is 0, p is equal to s. We'll loop as long as n is less than the length. We'll increase n, and p will be equal to p next. I wonder if it's this thing. P token, contents text token value. Because we might not have a token. So let's check that we have a P token type. Then we do this. Otherwise, 0. Maybe it's just type. Okay. So let's see where it segfaults this time. Still in print stack. At the same location. So that's not a problem. Well, this should be a string. Maybe this is a better option. But I'm not sure it's that this is the problem. Let's assert that we have an S and an S length. Oh. Pointer type mismatch. Expression has int 8, right? We need to do this. Alright, so this assertion fails. Let's split it up into 2 lines. So we check both that we have an S and that we have a length. We don't have an S. Interesting. So if we have new, we'll do this. Otherwise, push failed. Okay, so why does push return a 0? Or more interestingly, what can make push return a 0? Well, if stack copy fails, we return a 0. If we don't have a last, so if this index fails, we return a 0. Let's just add a temporary thing here so we know what we're dealing with. If we don't have an S, like so. And I don't put it inside of this because I want to be able to delete it easier. Okay, so this is not the place. Alright, so our index function fails when we give it a -1. So if index is less than 0, which it is, we set n to 0, p to find last, as long as n is more than the index. So first it's 0, which is more than -1. And then it will be 1 less, which is -1. And -1 is not more than -1. So we should do one iteration. And p is equal to the previous. Maybe we could do something like if s length is equal to 1, we early return s. Okay, look at this. Isn't it beautiful? So we have a stack of size 2 with an entry at this location. We have an HTML. Next is pointing to this address, which is this entry. Preview is 0. And this first one is an HTML, the second one is body. Next is 0. Previous is this 2500, which is this entry. It works perfectly. Let's remove those, this warning thing. Wait a second, it works, but it's segfaults. Is it our garbage collector that segfaults? Yes. And I think I know what it is. inside of our push, let's not run the garbage collector. Let's do that manually at the calling site instead. Like here. Okay, now it works perfectly. Alright, so now we are successfully able to build a stack of HTML entries. So now we just need to start parsing. And that's our next logical step. If you like this episode, please like and subscribe. And thanks for watching. Thanks for today. What's up, guys? Welcome to today's show. So today we are going to continue our HTML project. Last time we managed to get the parser's push function working. But we also need to make our other basic operation, which is the apop operation. So that's what we're going to focus on today. And before we can successfully apop something, we need to, let's see. Well, the apop function is going to pop something off our stack of HTML tags and tokens. So we need to be able to remove something from our list, but we need to be careful, because if we remove the first thing in the list, then we need to update the length, right? But perhaps we don't have to care so much about that, since we are going to be working on a new copy of the stack. So let's see. What we do need, however, is a way to filter something. Well, I think this will not be that difficult after all. Let's start writing the function and see where we go. I want to create a macro first, because we need to know if the current position in the list is the first of the list. So let's create a first macro that takes an X. And what we want to check, if does this X have a previous field which is 0. If this is true, then we are at the first position in the list. So let's see, apop, garbage stack, token type. Right, we want to pop off the last thing in the list of that type. Yeah. So we need to start at the last position and take it from there. Alright, so we'll have a stack, a pop. We need some kind of tuple structure, by the way. Let's call this a S tuple for stack tuple. And this will return a pointer to a new stack, X's, and a token, X. Similar to our other tuples. And we'll type def this struct S tuple to an S tuple like this. Right? So let our a pop return that instead. S tuple. And I don't think it needs to be a pointer. No. Sometimes it's easier without pointers, actually. Even though I really love pointers. Alright, so this will be an S tuple, a pop. We take a garbage G. We take a stack S. And we need a token type. Alright, we need some stack pointer. We need to assert at least that we have a stack with a length and a type. So let's make two cases. If our stack is currently at a length of 1, in that case we want an entirely new stack. Wait a second. In that case, the stack will become empty, and we don't really use empty stacks. I think I want to change one thing. Let's return a pointer after all, so we don't go into the land of static again and everything falls apart. So we need to have an S tuple for the return value. And we need a size. So the size will be the size of a struct S tuple. And we can malloc our return value at this point. And we can assert that we have a return value. Okay, so if our length is 1, then we basically want to return the first token, or the only token. But we still want to make a copy. So let's have a stack new, or let's say S prime. So we follow the standard we have built this far. And in all cases we want to make a copy. So set S prime to stack copy. We give the G and we give the S. If we don't have an S, we wanna go to the error case. Which we'll define down here. And how do we signal that this is an error? Well, we will take the return values x's and set to 0. And let's also set the type to 0. Okay. But if we have a new copy with a size of 1, in that case we want to return that. No, in that case we want to return an empty stack to signal that that the stack is empty. But it's not an error case, so because we will have, wait a second, we don't have a type, we have a token with the type. So we need to do something like this: x dot type is 0. That means an error. However, in this case, we do get a token back. So we will copy that token to our return structure. So we'll do a memory copy into our our return token X from our S prime token using the size of a struct S token. So this is what we'll do. So we return this token from the stack. And we also want to garbage collect in case we have a G. So let's add our S prime to the garbage collector. Let's also have an end here. Like this. Okay, so this is the case in if we have a stack length of 1. But in all other cases, we want to take that copy of the stack and pop off the last one that matches our token type. Right, we also need to check that the type is accurate in the case of 1. So if our S prime has a token and that token has a type which is not equal to the type we're looking for, in that case it's a parse error. So we go to error. This is really low-level procedural, almost assembly code. But I think it's the easiest way to write this kind of function. The structure is pretty good anyway. Alright, so let's set our pointer to find last of our new stack. And then we will loop backwards from there until let's see. Maybe it's easier to use our minus thing. So let's create a signed short integer of type of name n. So we'll have a for loop where we set n equal to -1. So that's the last thing in the list. We'll also set our pointer equal to we'll index into this S using n as an index. And we want to loop We want to loop once for every location in the list. So let's also create a regular int that we zero initialize. And we want to loop as long as x is less than the current length of the list. And each iteration, we want x to increase, n to decrease, and p to be equal to the new index of n, like this. Let's add a second prerequisite. So x must be less than this, so we don't crash. But as soon as we find a token of the correct type, so let's check if p token and its type. Let's see, we're going to loop as long as it's not equal to the type. But when it is, we will break off. So then we won't really need a body of this for loop. Let's just do an if statement when we are done. And we'll check if the token type is equal to our type. If it still isn't, then it's a parse error, and we go to error. Otherwise, we have found our token, and we want to memory copy that into our return token from p token. And let's cast this correctly, since we're doing a byte by byte copy. And struct s tuple. No, struct s token. But we do also need to pop off this thing from the stack list. So we need to check if what p is currently pointing to we want to check if it's the last thing in the list. So if next is 0, then this is the last thing of the list. And if it's the last thing of the list, we want to take the previous thing and set that next to 0, because we want to remove the last thing. We will also take the length of the list and decrease it. If we have a G, we want to add to our garbage collector the last thing on the list. And we want to set X's to our new stack list. Is this all we need to do? Let's see. If we set next to 0 and we make the list one step smaller, then we have effectively removed the last thing. However, if P does not have a previous, if it's the first thing of the list, what do we want to do in this case? So if previous is 0, we want to pop off the first thing of the list. So basically the second thing will be the new list. Let's start there. We set X's to P next. And we'll set the previous to 0, since this is a new first. And we need to copy the length. From the old list. And decrease it by 1. By the way, let's do this. Let's also garbage collect if we have a G. In this case, we want to set give the old list to the garbage collector. And that's just about it. And in all other cases, we are somewhere in the middle of the list. So what do we do in that case? We want to take the previous and set it to next. So we jump over the P. And we want to set the next. Let's see, we want to set the preview of the next. So let's see. The next previews should be the P previous. I must make this graphical. I think it's a little bit complicated. So we have 1, 2, 3, 4, 5, let's say. And we're at this position. So we want to pop off this. So this is P. This 3 here. P previous is this 2. We want to take its next and set to P next, which is a 4. And we want to take the next previous and set to this. All right, this is correct. So we effectively jump over our current position. And then we take the length and decrease it. And we set our return value to this stack. And go to end. Okay, a lot of moving parts in this function. I hope we will get it to work. By the way, it's not enough to just compare the token type. We need to compare its value, because if we encounter an ending body tag, we want to remove the corresponding open tag. Yeah, need to change this up a little bit. Instead of having a token type, let's see, if we go to our tokens, this is what is interesting. We want a specific tag. Well, the type is the tag. Well, alright, so the token itself has a token type, but the actual tags, they have a tag which is one of these. So let's alter this a little bit. Then we can, instead of saying token type, we can say tag. So let's still call it a type, but we need to compare it a little differently. So we want to check the S token contents and the start tag type. This is what we want to compare. And same here. So token contents start type. Token contents start type. Okay. I think this is going to work. We will probably need to alter it a little bit, but I at least hope the general idea is going to work. So we can't just do this. We need to signal the error by saying that this token, its contents start type. That's what we'll set to 0. A little bit complicated, but it's how it's got to be. Since we can return an empty stack. And that's not an error necessarily. Okay, so how do we test this thing? What do we have this far? We have this HTML, and we push on the HTML in the body. So let's try to pop off a body tag. So let's do this. No, not this. We'll create an S-tuple. Let's just call it tuple for now. We'll set our tuple equal to a pop, and we give the stack the garbage collector, the stack, and the tag that we want is body, let's say. So that will pop off something in the middle. That's good. No, it's the last thing. We do only have 2 tokens. Maybe we should do something like this and push on T+2. So we have a text token at the end as well. All right. So let's first check if we have an error. So if we don't have a tuple x contents start type, then a pop failed. Otherwise, let's print that type. So let's call it S tuple type is equal to this tuple x contents start type. And if we have a returned x's, that is a new list. Then we can print that list. So print stack tuple x's. Let's also add it to the GC. Okay, something like this. Let's see what happens. Unknown type name stack 17 in parser.h. We need to move this down a little bit. Okay. Conflicting types for APOP. S-tuple. Right, we need to make it a pointer. And those arrows again. I always seem to forget the arrow when it comes to the length, but not with the other things. Statement with no effect. What? That's weird. How does it conclude that? Ah, okay. This is what it should be. Not that many errors, but the behavior is more interesting. All right, let's see what happens. Okay, the assertion failed because push failed. Let's see, what are we doing here? We are creating a new stack of size 1, putting this to it. We push on t plus 1, which we're getting from this. Shouldn't we be able to push on a second one like this? What if we use 2 different pointers? Could that be something? So let's do new 1 is this. If we have a new 1, then the new will be created off of that. Will this make a difference? Weird. What can make the push fail? Because the first one seems to work. So it returns 0 if the stack copy failed. Or if we can't get at the last position. Let's just temporarily let this return a 1 instead. Will the push still fail? Hard to see because it crashes. Let's exit after this point in time. Okay, so now that it didn't fail, which means it returns a 1. So this is the problem. We are not able to index into -1. And what if we don't use the index, if we do find last instead? Will it make a difference? Sometimes it's good to have these unused utility functions from before. Okay, so we need to fix our index because that will be needed later on. But let's see what we get. Yeah, that's probably why this crashes, I guess. Let's make a mental note that we want to fix this. But I want to take one thing at a time. Actually, we need to fix it now. So if index is less than 0, what do? We set n to 0. We set p to finding the last. And as long as n is more than the index, we want to continue. And we set this to minus and this to p prev. So if we have 1, 2, 3, 4, 5, and we're going to want to go to -1. So at the first run, we have index is -1 and 0. And we're at this position. And then what happens? We decrease n, so it becomes -1, and we go one step back into this 4. But we should land on the 5, right? So what if we were to set n is equal to -1? Then this is our starting position and we're at the 5. But this would never be true. So we would have to do something like n is equal or n is less or equal to index. No. Let's try. So in this case, this is our starting position and we're at the 5. This holds. Then we do this, so we go at the 4, and will be this, and we break out of the loop. But we break out of the loop pointing at this 4. My head is spinning of all of this right now. What if we were to go back to what we had? We set this to 0. And as long as n is more than index, so n is 0, index is -1. So we're at the 5. This holds. Maybe we should put this inside of the body of the function instead. Will that make a difference? So we're at the 5. This is what we have. This holds. So we n minus minus. We first do this. So we go to the 4. It's basically the same thing, right? And if we were to do this, this, then we start at -1. So this is our starting position. We're at the 5. We check the precondition. It holds. We do this. Jump to the 4. I think we might need to make a while loop out, or a do loop out of this. So n is 0, p is find last of s, and we do n minus minus let's do this. We do n minus minus. And if n is less, if n is still more than the index, then we want to do this. So what happens if we run this? N is minus 1, index is minus 1. We set it to the last. We decrease this to minus 2. This does not hold. This it will not run. And n is n more than index. Is n less than index. Maybe less than equal to. Because now it is, no, I was right. Is n more than index? And it's not. So we break, and we have successfully gone to this 5. But what if we want to get at the 2? What happens then? Minus 2. So we start at this, n is minus 1. P equals find last. We're at the 5. We decrease n. So it's minus 2. By the way, index should be minus 2. If n is more than the index, maybe we should do this. If n is more than index, it is at this point. So we go to the previous, we're at the 4. We decrease n. Is it still more than the index? It is not, and we break off at number 4. So this works at number 4 and probably 3 too as well. But does it still work at the 5 with the reordering? If we want to go to index 1, minus 1. So we set n to minus 1. We find the last, we're at the 5. If n is more than index, it's not. We go to the previous, which we don't. We decrease n. Is n more than the index? It's not. We break. I think this is going to work. Let's try. Okay, at least we got one step closer. Let's see where it crashes now. If we go to GDB, imprint stack. But which print stack? Is it the first or the second? We have two new lines. Still hard to see. So let's do this. It's the first that crashes. And we have a stack of size 3. We print the first. We print the third. And then we crash. So we're still having problem with the push operation. Wait a second, we're trying to print the... No. And if we try to print new one instead, what happens? So it's like this is overwriting. It's overwriting this. Next is F0, and this is that. So when we push a third thing, it bugs out. Do a stack copy. We make a new entry. Find the last. And the last next should be entry. But have we set any previous for entry? No. Oh, we do that here, never mind. So last next should be entry. Entry previous should be last. And we increase the size. Which it does. And the previous of this is this. And the next of this is this. So it's like it's not finding the last one. Because this is the new thing. And the previous should not be the first. It should be the second. So it's like find last is returning HTML. Let's add a temporary thing here. Like so. And let's change this back to new. And let's add a new line to this debug thing. Okay, last is HTML. At this first occasion, that is accurate. But at the second one, it's not. So how do we do the find last? P is equal to S, as long as we have a P. P is equal to P next. What if we were to do this? Let's try this. Okay, this looks better. Last is HTML, last is body. So we get this thing from the beginning. That's good. But we still crash, but now at a different location. APOP. So let's see. Don't have any function calls here, but we're at 350, so it's probably pretty far down. We have a memory copy. So where do we have memory copies? Memory copy. Well, in several places. But let's see, we make a copy of the stack. So the stack is, it has 3 entries. So length is not equal to 1. We can skip this part. We set x to 0. Set n to -1. And we set p indexing into -1. So that's the last one. Is x less than 3? Yes, it is. And is the last token not of the correct type? It's also true. So we increase x to 1, decrease n to -2, and we go to that index. And then we're at the body tag. So this will not hold any longer. So then we'll do the memory copy, but we crash before that. I think I need to do this graphically again. So first, let's see, it's a size 3. So we're going to go through 5, 4, 5, 4, 3. And this will be -1, -2, -3. Let's try making this function a little bit, this loop a little bit easier. We'll set x to 0. We don't care about the n. We set p equal to find last of s prime. As long as x is less than the s prime, then length will increase x, and we'll set p equal to the previous. And if p token contents start type is equal to our type, in that case we break. So this is a little simplification. Let's see if it changes anything. Doesn't seem like, but let's double check. Need to reset my terminal. It still fails at the same location. So let's do something like this. We don't print any of those. So maybe we are failing all the way up here. Is that possible? What are we comparing here? We jump somewhere. Compare EBP 10 to EX. Why do we end it by 7? I wonder if we are... Let's do this instead. X30I EIP. No, it still does the same. EP plus 10. It points to somewhere on the stack where we have a 2, so that's the length. But shouldn't the length be 3? Maybe this is what's the problem. No. Alright, so this happens. This is why you shouldn't use go-to. It's a tricky thing to debug. Okay, so this is fine too. Six, seven, and then crash. 6, 7. Crash. So this comparison is what crashes. P is 0. Because we have this. And the length is 3. So x0, x1, x2. And when x gets 3, is x, as long as x is less than s prime length. And p is fine last. And 1, 2, 3. Maybe we should have one more pointer. Let's have a last like we did before. What if we were to do something like this then? Okay, this is a different result. So now we get 6, 7. P is equal to this. And the next thing we get is a 5. So P is equal to HTML. Maybe we should have P here after all. This doesn't happen. Okay, that should give us a little bit more info. So we're scanning for type 2. The type is 0 for all of these 3. So that is a problem. Maybe this is how we should show an error. Because we can't really point to something that is not there. So let's check that instead. If the start is 0, then this fails. But why are all these types 0? That must be a problem inside of our make token, I suppose. So what happens inside of make tag start? We set the type to tag start, but we do not set the type inside of the contents. Or do we? That's our P. So we need to do P type is equal to Find type. And this should be based on the value. Yeah. And that's true for the make tag start, tag end, and self-closed. And we need to write that function, find type. That should return a tag. We'll take a regular string. So we need some kind of global state for that, or at least a constant. And I guess we need a structure for the map. Where we'll go from the string to the tag. So let's do something like map, tag map, array is equal to so what do we have? HTML body B and BR. Something like this. And now we can write the function. How did I tag find type, and it's going to take an int date. And we'll traverse this array. So we need a string compare function. And we need a min function. Define min of x and y. If x is less than y, we return x. If x is less than y, then we return x. Otherwise, we check if y let's just do this. If x is less than y, return x, otherwise y. And here it's important to address everything in parentheses, because we might have an expression for this. Something like this. Now we can write a string compare function. So bool string compare, we take an int 8x and int 8y. We create the max and an n. And we set the max equal to the min of the two lengths. So the min of string len x, string len y, and this is just as a safety precaution so we don't compare too much and overflow the thing. So we do a for loop. We set n equal to the max. As long as we have an n minus minus, we'll also set px equal to x and py equal to y. And we'll increase both of them to each iteration. And if px is not equal to py, we can early return. Otherwise, we need to check after the loop if n is equal to max. Which means we have compared the thing without finding anything bad. So we can return true. Otherwise, something is weird. No, we don't need this, I guess. I think this is right. Oh, pointer targets in int 8. What did I do now? So where is that thing? Tokens here. Can we do this? I'm not sure. Yeah. 28 Hyperbird C. Right, we haven't really written this thing yet. So, let's see. If string compare, and this will return true if the two strings are equal. And we need to check the tag map at index n. And the string. And we compare this to the string that we provide to the function. If those are the same, we can return the tag map of n. Tag map of n dot tag. Otherwise we'll return an error, which is 0. Too few arguments. There. Multiple definition of tag map. We include it from several places. So we need to move this. Let's put it on top here. No. Phew. Something like this. Okay, it compiled. Okay, we got a little bit closer. This time we actually find the body tag. And we go to 7 before 5 and then 4. But APOP still fails. So what's at 7? It's this part. If p token content start type is not equal to type. But I'm not sure I should do this any longer. Should I? Let's try it this way. Okay. So S tuple type is 2, stack of size 2. We have the HTML and we have the ABC. And we have popped off the body, right? Well, that's cool. So what if we were to pop up the last thing? Will it still work? Or the first thing, for that matter. So if we just have a stack of 2, so we'll set new equal to this. Comment this out. And we still want the body, but this time it's the last thing. Seems to work. But what about the first thing? So let's put this back. And let's say we want to do an a pop for the HTML, which is the first thing. What happens then? Body ABC. Yes. It works. It works. What about if we pop up the absolutely last thing? If we only have a list of 1. So basically we run this against old. Then we get the tag and an empty stack. This is perfect. Really perfect. So let's just clean up a little bit. Remove some printfs. Sometimes it takes a long time to write something, and you get doubts a couple of times along the way. Will I ever be able to accomplish this? But more often than not, the answer is yes. '60 and '61 in the parser. N and last. Very nice. So now that we have our apop function, the only thing left is to write the parser function and handle the function calls related to the tags. So thanks for watching. Thanks for today. What's up, guys? Welcome to today's show. So today we are going to define the grammar of our language. We are going to continue creating an HTML language in C, and this is an important part of creating your own language or writing a compiler. So there are different ways to define this, but I am going to do it based on something which is called Bacchus Nauer form. And that looks like this. So to the left we have symbols, and those symbols resolve to something on the right. So this is called a production rule. Let me just change this to MDF, BMF. So this symbol means that this to the left should be replaced to this to the right. And this line is called a production rule. And this defines the grammar of your language. And that's what you use later on when you are parsing symbols. So our minimal version of HTML will basically look like this. We will have a root symbol, which is called document. And the document contains a head and a body. And this is not the HTML tag head, even though it looks similar. It is the symbol head, which contains other things. So, for instance, the head will contain the string head, followed by the symbol title and the string slash head, like this. Whereas the title in turn is similarly the string title followed by a string followed by the closing title tag. So this is the entire head of our minimal HTML language. Then we have the body, the symbol body, and that will in turn contain the string body, but then it gets a little bit more complicated. We will have a list of tokens, and then the ending body tag. And these curly braces means that this inside of that will be repeated. So these are several tokens. And what is a token? Well, in our case, it is either a tag or a text token. So this vertical bar, the pipe sign, will means or. So tag or text token. Whereas the tag can be in our case, it can be either the B tag or the BR. That is the only thing we have defined this far. The text token, well, that's just a string. And the data type string, I type like this, with a capital S and no braces around. And this means that this is not going to translate to anything. This is a top or a bottom layer kind of thing. The B tag is the string B followed by a token, one or several tokens, because this can be both text token and other tags. And then we close the B. And our BR, well, that's just the string BR, like this, indicating that this is a self-closed tag. So this is our entire language, defined in Bacchus-Naur form. And we're not programmatically going to use this when we parse, but we will use it as a guide when we code our parser. So you should always define the grammar in one form or another, so you have something to fall back on when you code the actual parser, which is the next logical step. If you like this episode, please like and subscribe. And thank you for watching, and thanks for today. What's up, guys? Welcome to today's show. So, last time we managed to get our two stack operations working, push and a pop, and we were able to print this stack. I'm gonna start by cleaning up the printf statements a little bit. We don't need this, and I'm gonna make this print stack a little bit simpler. Let's only print let's see. Let's only do something like this. And then the token, what's it gonna be? It's gonna be the P token contents star tag value. And then after the loop, we're gonna just print a new line character. But I'll save this code if we need to debug it later on. I saw something else. Where was it? Right. Let's remove this thing, and we don't need this either. And this loop we're not going to use any longer. And this old code, well, we don't need it either. I think. Yeah, we have a new stack copy and so on and so forth. Alright, so now it's a little bit cleaner. Let's just see how it looks if we compile this thing and we run it. Yeah, so we have a stack of size 3 that looks like this. Yeah, this ABC shouldn't be there. Later on when we parse, I'm not going to include the text tokens, so it'll be fine. And in this case, we have popped off the body. Yeah, it works. Alright, so let's see what's the logical next step. Well, we need to have a function that checks if a specific HTML tag is open, so to speak, if it's on the stack. So let's write a function like that. Parser h. So this will return a bool, and let's see, we can call it is open, and we are going to give a stack. I think that should be enough. So let's go here and write this function. So bool is open, and we have a stack s. So we need to iterate through the entire stack. So let's have an int16 n and a stack p. Let's assert that we have a stack and that the stack has a length. Or let's assert that we have a stack, but if it does not have a length, we can return false early. Otherwise, we do a for loop. Let's also have a bool for the return value. And the return value will be false from the beginning. And we set n to 0. Our pointer will be equal to the s. We loop as long as n is less than s length. And we increase n. And we set p to p next. So let's see. Do we have a string compare function? I don't really remember. Yes, we do. So so if string compare, right, we need to give a tag that we're looking for. So we need to have something like, is it tag type? Need to look in the H file. Maybe it's in the tokens. So we have these. Right, we can check that instead of a string compare. More optimized too. So we will give tag type, and let's update the H file before I forget. So tag So instead of a string compare, we just do if type is equal to p token type, I guess. Let's double check. So if we have a token, okay, that's the token type. We need to go one step later, more thorough. So token dot contents dot and this is going to be a star token type. This is what we're going to compare. If these are the same, then we can set ret equal to true, and we can break. Otherwise, we can continue iterating, and then we return ret. Simple enough. Let's double check that this works. So in our example main that we have, let's see, HTML body. Okay, so let's see. So before we start popping off stuff, let's do something like if it's open, new is the name of the stack, and let's say we check for body tag. Let's also print an else message. So we do this once, but we do it once again after we have popped off that body tag. And at this point, the stack is called, let's see, tuple x's, I suppose. Let's try this. This should not be a semicolon, it should be a regular one. A comma, that is. Okay, compile. Bodies on the stack. No body. Alright, cool, it works. So I'm thinking, are we ready to code the actual parse function, or do we need any other utility function? Think we're ready. If not, we will see. Okay, so how to do this? This will be the last complicated function in this whole project. When we parse, what do we want to return? We want to get a stack back, right? So it'll be stack parse, and let's just check that we don't already have a parse function. No. Okay, so what do we need to give it? We probably need to give it the garbage collector, right? Or maybe we could let the parse function itself create one. So let's not. But what else? What are we parsing? We are parsing a string from the beginning, right? Or should we just start by writing the function that parses the tokens? Let's start with a string. And perhaps that is all we need. No, let's do the tokens. So we give it a tokens star. And let's start there. We might have to add some stuff later. And we also need to have a parse prime function, which it's a little bit more complicated. And this will need a garbage collector. It will need a tokens star. It will need a current stack. Yeah. So the parse function will basically just initialize and kick off the parse prime function, like we did with Elixir, in a functional kind of way. Alright, so let's see. We have stack and we have the parse function, which takes a tokens star. Let's call it x's. And we need a garbage g. stack. What else did we put in the signature? Garbage tokens stack. And we need to assert that we have token. And also that we have a length. We will create the garbage collector. Make garbage. And we need to create an empty stack. Or how did we write that? Maybe we start with one stack. How did we do this? T is equal to, no, x's is equal to lexer. So that is the token structure. What about the stack? So we make a stack. And then we copy the first token. Alright, let's do that. This means that we need to have two stacks. Let's call them old and new. So the old will be equal to make stack. And we need to specify a size. How did we do it here? Size of 1, alright? And let's assert that we do get a stack back and that it has a length. And since the axis has a length, we know that we have at least one token. So let's copy that token there. So we need a T. What's a T? That's a token star. So T will be equal to the old. Oh, will be equal to X's T's. Do we have some pop function or similar for tokens structures? T get. Alright, so this takes a token's structure. What does it do? Makes a copy of the old one. Increases t's and decreases the length. I think this is what we want. So it chops off the first token and it returns it along with a new token structure. So that's perfect. See, it's very, very nice to have all these utility functions. And this would be a tuple. So maybe we should wait with setting this t and instead set our tuple equal to tget with our garbage collector and our x's. And how do we check for errors? It returns an empty tuple. So if both x's and x, let's see, x's, if both of them are 0, then, or any of them actually. So let's check if tuple x is 0. And we return 0. Otherwise, we want to copy this thing. Let's set t equal to the tuples well, x is our token, so that's what we want. Right. So let's make a stack. Or let's see. Why did we need an old stack and a new stack? Can't really remember. But we have one memory location inside of the old, so let's use it. So we need to do a memory copy into, let's see, the old token. And we're going to copy the new token. And I guess it's size of struct as token. Let's double check with our main function. So into this, we copy this, size of this. All right. It's good. So we need to check if there are any more tokens or if we're done. So basically we'll do something like if tuple x's length, if this now is 0, then we can just return our whole stack. But I'm not sure what I was thinking with the old and the new stack, because this is the only thing we're going to pass on. Because here we get a new stack when we push something onto it. Okay, that was probably what I was thinking. Let's rename this so we don't get confused later on. Let's remove this new thing and let's just call this S. We need to have the old name so we get the highlights. So we have S and S. And S. S and S, like so. The parse prime function will contain a new one. Alright, so maybe we should have kept old and new, but let's do S and S prime. We have used that syntax as well. Okay, so now we have successfully parsed the first token. And if there aren't any more tokens in the list, we just return it. But if there are several, then we need to call our parse prime function. So basically this S prime will be equal to parse prime, and we have a garbage collector, we have a tokens star, and that's the new tokens star, which is the tuple x's. And then we need to pass the stack that we have, which is S. And if this somehow returns an error, then we can just return the S that we have. But otherwise, we should be able to just garbage collect and then return our S prime. I think that's enough. Alright, that wasn't too difficult. Now to the parse prime function, which is a recursive function. So this will probably be a bit more difficult, but we'll see where we end up. So we'll have a stack parse prime, which should be a pointer. And this takes a garbage G and a token structure, X's, and a stack. Alright, so what are we going to do? Let's first check if the token's structure is empty. Well, we need to assert that we have a stack and that this stack has a length. Then we can check if X's has a length, and if not, we are done, and we can return this stack. However, if X's does have a length, let's see how we did it here. We used the push to get the new stack. Well, we can basically just use our tget to get a token and our push to get the new stack. Maybe this is not so complicated after all. Let's say we have a tokens X's prime and we have a stack S prime. We also need to have token T and a T tuple. So the first thing we need to do is to get the next token. So the tuple will be equal to tget with our garbage collector and our X's. And if this for some reason is empty, then we need to return an error, I suppose, a parse error. But if we get something back, that will basically be our axis prime. So let's be thorough and set it to, did I call this the wrong thing? Yeah. Tuple axis. That's our new axis. Our T is our tuple X. And then we can just push this to the stack. So let's see. Our S prime will be equal to push. We give the garbage, we give the old stack, and we give the token. If we do not get a stack back, we will return a parse error. But if we do, we can recurse, which means we're going to return our self with our garbage collector, our new axis, and our new S prime. Okay, this wasn't so tough after all. But we do only want to parse the open tags, because that is what we are looking for. Do we have a peak function for tokens? Maybe we should have. Let's see. If we get a open tag, then we want to add it to the stack. But if we get the text token, we want to handle that differently, don't we? Or maybe we could think about this a little differently. We could parse everything like we were thinking. Choices, choices. I think we need to do this a little bit differently, don't we? Well, let's start by doing it this way. So let's just ignore the other tags, the other tokens than start tags. And how do we do that? Well, the easiest way will just be to we check if the token type is equal to start. That's the type of token, right? Because here are the different tags, but token type. Yeah, we have text. Okay, tag start. And this is what's inside of the token. So yes, if this is equal to tag start, then we return this. Otherwise, we return parse with G, but let's see. We still return x as prime, but we return the old stack, so the stack without this token. And that way we're only going to parse these. And this is a little bit problematic though, because we parse the first token manually instead of this function. And if this were not to be a tag start, we cannot pass on an empty stack, because that will mess things up. Anyhow, the standard says that HTML should always be the first tag. So we can actually we can actually assert that T type is equal to tag start. That's a good enough solution, I think. Okie dokes. Okay, so let's see. We make string with this. We'll exit. T is equal to x is t's. So let's do s is equal to parse, and we give the x's. If we don't have an s, or let's assert that we have an s, and then we print stack s and exit. Assignment to string star from incompatible pointer type stack star. 510. It's here. Okay, our S is called string. What's our stack called? Old, new, and new one, alright. So let's call this old then. Okay. Incompatible types. T-tuple from type T-tuple. Okay, so it doesn't return a pointer 255. So let's not make this a pointer. Tuple is equal to blah blah. This should be a dot. 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 And I guess we need to do the same here. Wrong type argument. If tuple dot x. So what is the x in a t-tuple? T-tuple. That's a token without the star. Okay. So let's do the check for x's instead. The rest should be fine, I suppose. T is equal to tuple dot x. Okay. Okay. Well, let's not even use this T then. Let's see, we use it here and here. So let's go to tuple.x instead. And same here, tuple dot x. I guess we need to do this then. Same here. So t is equal to token blah blah blah. We push the tuple.x directly. And we can't do this, so we need to do tuple.x type instead. Yeah. Two, 5, 8. Well, we need to have a dot here. And here. Cannot convert to a pointer type. How did we do it here? T is equal to x's t's. X's t's. Did I forget one level? Tuple x type. Tuple x is. Should it be tuple.x? Let's see, x's is a tokens star returned by the lexer. And t is x's t's. But that's why in this case we go at it directly. And we are using the tget function. And it returns a cheat tuple. With a current token and a list of tokens. And our push takes a token. What if we just do this? Well, let's jump over this for now and go to 280. Do we need to go over the river for water? Let's create a void and a token star t, where our void is equal to void star the address of tuple x, and where our t is equal to token star v, and then we give $1T. Am I troubleshooting the wrong argument? S token. That's the problem. We need to put this ampersand. Alright, let's remove those two. This and this. This and this. And we put this right here. And this should be the address of tuple X. Alright, that's better. Let's see what we get. Oops, segmentation fault. And it's the printing that fails, right? Maybe we should assert that we have a length as well. It still crashes. What if we did something like this? And we only have this HTML tag. Will it still crash? Yes. And we do have an axis. What if we assert that we have an axis length as well? I wonder at what stage it crashes. Well, this doesn't give us much. Let's try GDB. So we run F and we run start. Continue. Tget is crashing. How can this possibly crash? So it's a bit from the make token. Is it so here somewhere? What? Well, here is the assert. And here are some if statements. This, I guess. And then we move some data around. I guess for preparing for the call to make token. So somewhere, some of these arguments, I suppose. We know that we have an old tokens with a length. So it should have a tease. It should have a type. An old tease. Content text token value. What did EX contain? This looks like a string, I think. NF1 underscore. Maybe this is the problem. maybe this value is just random data, uninitialized data. Am I sending the wrong arguments to tget, perhaps? I'm sending the x's. And we have asserted that we have an axis with a length. And what do we give the parse function? We give it the output from the lexer. Maybe it's some problem with only having one tag. So now it worked. Okay, so we need to make sure that we have an HTML. And I think I know why it crashes, by the way. Because if we parse something which is not an open tag, it crashes. And that must be because of this. The only difference is we send the S instead of the S prime, which should be okay, but perhaps we garbage collect this one, but not this one. That must be it. So how do we make sure we don't garbage collect that thing? Maybe the easiest way is just to make a copy. So S prime prime. So in this case we set S prime prime equal to stack copy garbage and the S, and then we give the S prime prime here instead. Okay, and let's give back this original thing. And it works, because we're only interested in the open tags, and these are the only open tags. So if we, for instance, would have put a thing like this, we should also get the B. Yes, works. All right, great. So now we have a parser. All that is left to do is to make this program parse through the open tags, and then we use that stack to call a function for each tag. Each tag will have its own function, and we will call that function on this input and work with this string in different kinds, depending on if it's bold or whatever. All right, that's a good enough time to stop. If you like this episode, please like and subscribe. Thank you for watching, and thanks for tonight.